Good morning, good afternoon, everyone. Welcome to Keysight Technologies virtual event series. We are pleased to have you here for today's virtual event on Demystify 800G hyperscale testing tips and tricks. My name is Girish Baliga from Keysight Marketing and I am the presenter at today's webinar. Today we'll be spending the next 45 minutes or so talking about demystifying 800G hyperscale testing tips and tricks. Before we get started, couple of housekeeping inputs. During the presentation, you can dial in your questions in the Q&A box on the streaming console. We'll be more than happy to answer your questions and get back. Also, please share your recommendations on the survey form, which will appear as a pop-up during the course of the webinar. There's also a resource collateral on 800G test technology, which is available on the webinar console. You can download these as well from the resource list. In addition, please share your comments about the program enabling us to serve you better. And please use audio headset or earphones to listen to the virtual event audio for good audio effect. Before I get started, a short introduction. I work in the marketing organization at Keysight Technologies, the marketing manager and lead marketing efforts for 5G wireless data center infrastructure, high-speed digital, wireline business, as well as aerospace defense business segments. Without much ado, let's begin the session. As we see from the graphic, the overall data center infrastructure market is growing quickly. By the year 2024, it is expected to grow to 90 billion US dollars. Part of that growth will be from the optical equipment market, which is supposed to grow to 16 billion by the end of this year, as well as from the transceiver market, which is expected to grow to around 12 billion by 2023. Data center infrastructure is constantly evolving. Emerging technologies such as 5G, artificial intelligence, virtual reality, Internet of Things, and autonomous vehicles generate explosive amount of data in the network, creating new computing and performance demands in the data center. There are six key trends driving the computing and data center industry. Let's talk about them one by one. Let's first start with the obvious overarching driver in the communications ecosystem, which is helping in the explosion of in data growth. If you take a pick of industry reports or from your favorite industry analyst, you would see that the explosion in data growth is clear. As we know, it was not too long ago that voice traffic dominated the communications traffic. Now it is video, and moving forward, it would be virtual reality, autonomous driving, and a host of new IoT applications and sensors. So in effect, data is exploding and mobile is going to drive this growth exponentially. On the flip side, as you can see, the total operator capex and opex spending on the network infrastructure to support all of this is flat or declining. Price points of any new infrastructure which is flowing into the environment are quickly commoditized, and the price points are driven down by 20% to 30% a year. So to handle this challenge, the operators, the service providers are increasingly applying data center and cloud network principles and technologies. These principles involve moving functionality into software through the SDN and NFV, and then leveraging the bare metal servers and cloud compute to scale with the data center economics. That has been true for the core network already, but the same level of virtualization is coming to the RAN or radio access networks with the move from 4G to 5G. The impact to major wireless infrastructure vendors is huge. Previously, the bulk of the business was proprietary hardware platforms with the large custom ASICs, and very nice profit margins, but it's no longer so. Their customers are forcing them to leverage standard compute platforms with more open, much cheaper and dynamically reconfigurable NEMs. And they are in a revolution with the 10x to 50x magnitude cost reductions. In addition, as you can see, there are other significant factors like there are new technologies which need to reach faster speeds. For example, to reach speeds like say 800 GE in the data center, pulse amplitude modulation techniques like PAM4, PAM6, PAM8, PAM16 and so on are needed to effectively double the data throughout the NRZ signaling. Coherent optical data transmission is expanding from low volume niche applications such as long haul networks where performance is more important than cost to high volume applications such as metro networks, data center interconnects and even access networks. That said, the new standards such as Gen Z and C6 are being introduced that are tailored for specific tasks. The challenge of developing and introducing these new technologies is significant and expensive. So the whole world is connected and the pace of communication innovation is accelerating as the end users demand faster, more responsive and more reliable connections. Communication links are both wired and wireless, covering everything from Ethernet, optical fiber, cellular wireless, and other wireless data communications such as Wi-Fi. Test increasingly needs to span several of these domains, measuring from a baseband cellular signal to a radiated over-the-air waveform. End-to-end measurements may originate from handheld user equipment and to be evaluated at an internet data center, for instance. So, Keysight Technologies is at the forefront of providing the test methodologies through our innovative solutions for the most complicated challenges spanning the entire commercial communication ecosystem. You need to test your cutting edge designs across all product development stages from design and simulation to analysis to debug and compliance test. Keysight helps uncover problems at every stage and then optimize the performance and accelerate speed to market of your new products and solutions. At each phase of the product development life cycle, Keysight Technologies solutions help address your data center infrastructure challenges, and we would help you shorten your design life cycle by dramatically improving the productivity and ensuring the quality, thereby significantly reducing costs. Our data center infrastructure solutions covers all the network layers, starting from the physical layer 1 test to fully test the network all the way to layer 2 to 7, including software defined networking or SDN, as well as network function virtualization or NFV, validation and traffic loading. So we help accelerate data center infrastructure innovation so that you can focus on fast deployment of new services. As you can see from this slide, at the core of every network upgrade is the transceiver, and at the core of every transceiver is the channel capacity. Traditionally, data center operators tend to upgrade their network architecture every couple of years. However, many data centers are currently working at maximum capacity, and data center operator need to find a way to increase their channel bandwidth to reach speeds like 800G and above, as well as cost effectively. They need to ensure that interoperability of devices from different vendors are met. The move from 100G to 400G to 800G and beyond in the data center is revolutionary and not just evolutionary. Optical transceivers will need to use the advanced signal modulation and coding methodologies to reach such high speeds. These techniques would create new test challenges for transceiver manufacturers. And we are happy to state that Keysight Technologies has solutions that can help transceiver manufacturers address these challenges. Data center operators need to increase channel capacity so as to transition from 100G to 400G to 800G and beyond. This can be achieved with optical transceivers that use advanced modulation and coding techniques. Today, as all of us know, NRZ is the most common signal modulation scheme for 100G. However, as the speeds of NRZ designs increase about 28 Gbps, the channel loss becomes a very limiting factor. So a new scheme which is used is called pulse amplitude modulation, or PAM. And PAM4 is the recommended method to move to 400G speeds as well as higher data rates in the data center. Technically speaking, PAM designs are far more susceptible to noise. So forward error correction, or FEC, is typically used to correct for the channel errors in PAM links and is strictly considered for PAM testing. As you can see, the designer would require to make new measurements to characterize the impairments that were not previously an issue with the NRZ designs. And Keysight's test methodologies will ensure accurate and repeatable results to accelerate the development of PAM-based designs, which would include things like interface components and systems. Keysight's PAM solutions can help you every step of the way, like I mentioned earlier, starting from design simulation, transmitter and receiver test, channel characterization, and all the way to manufacturing test. Let us look at PAM4 and FEC in a bit more detail. As we all know, NRZ signal modulation is a two-state transmission system, and old-timers would know this is also known as the pulse amplitude modulation 2, or PAM2. While 100 gig requires 4 lanes of 25 gigabits per second NRZ modulated signals, however, as NRZ has gradually evolved over the last 50 years, with the improved speeds from 110 bits per second to 100 gigabit per second, many new concepts and challenges have already been researched and addressed. Transmitted signals using NRZ modulations are received without significant errors. As you can see, pulse amplitude modulation 4, or PAM4 signals use 4 amplitude levels to represent a symbol and effectively double the data rate. That's the throughput in the same bandwidth as NRZ. However, as I mentioned earlier, PAM4 designs are far more susceptible to noise, since an amplitude swing of 2 represents 4 signal levels. As a result, the signal to noise ratio, or SNR, is lower, and analyzing noise in transceiver designs becomes a very critical test factor. Forward error correction, or FEC, is integrated into the transmitted PAM4 signal so that it can be received without significant errors. Optical transceiver manufacturers must test to ensure their transceivers have strict compliance with the defined specifications and are interoperable with the other network components and transceivers from different vendors. Network downtime due to faulty transceivers is not an option for data center operators who have guaranteed service level agreements, or SLAs, with users. So Keysight's transmitter and receiver test solutions support the latest standards when it comes to this, whether it is 100G, 400G, 800G and beyond. Our industry experts are a part of the standards committees and work with the leading companies to develop next generation standards. Our test solutions ensure that your next gigabit devices comply to the required specification set by the industry standard bodies. Like most new technologies, the price of new optical transceivers tends to drop sharply after introduction to the market, and the development costs are amortized as the volume ramps. With the next generation transceiver technology like the 800 gig and above, it will reach mature pricing probably in a year or two after introduction. At maturity, the cost of transceivers is directly proportional to the complexity of the design and the number of optical components. The test times contribute significantly to the overall transceiver cost. More efficient testing of the broad range of transceiver data would ensure that it accelerates the innovation depending on the data rates and lowers the cost. The process begins in the research and development phase with the design of transceiver components and continues to the design and validation of the transceivers and then all the way through manufacturing test. At each phase of the product development life cycle, we do have test solutions that can be used to maximize the overall test efficiency. These tools can help shorten design cycles and also ensure that it dramatically improves productivity. And as we move forward, it would also ensure that it ensures quality and then significantly reduces the overall cost. With the 800G transceiver technology squarely on the horizon, data center operators are also looking for new ways to design and operate their networks so as to withstand the kind of traffic that billions of devices will generate. Many are shifting to virtualized networks using software-defined networking and or SDN, and also through network functions virtualization or NFV. As we know, software-defined network or SDN is a network architecture that would enable the network management and control through programmable, centrally controlled applications. And as we see, as the automation increases in the data center, it would drive new opportunities for all the layers, and specifically L4 to L7, typically speaking about application and security layers. And we also see that with SDN moving from the hands of early adopters all the way to the mainstream buyers, we expect the introduction of artificial intelligence techniques and machine learning to make the network more autonomous. And beyond 2021-22, we would see that the SDN enabled applications will become the most significant driver in the market, and they will become the most significant generator of profit for vendors, both in the SDN and the NFV market. The effectiveness of virtualized infrastructure and the network function can be difficult to evaluate. As one migrates to a virtual environment, ensuring that their virtualization deployment operates as expected requires a lot of complete traffic testing. Accelerating the HDN adoption using network test and emulation applications will help generate realistic workloads at realistic scales to validate cutting edge technologies and also accelerate the proof of concept and lab validation. When one has to support applications which are hosted in geographically separate multi-tenant virtualized environments like say a branch office or an enterprise data center or a hyperscaler, or it can even be the applications like a private or a public cloud or even a hybrid cloud, you cannot compromise the security, performance and end-to-end service, thus which impacts quality of experience. Network performance monitoring solutions typically ensure virtual network visibility to critical application data in these virtualized networks, and also with the offsite environments that help to reap the benefits of virtualized hyperscalers and data centers as well as SD-WANs. Let us now shift gears and understand more about our 224 Gbps solution for 800G research and pathfinding. 800G research and development labs are now working on the fastest and most complex signals the industry has ever seen. We will talk about the technicalities in greater detail in the ensuing slides. As you can see here, the Keysight's 224 Gbps solutions are designed to meet the state-of-the-art requirement of these leading-edge labs. For instance, our M8199A arbitrary waveform generator has twice the sampling rate and 50% more analog bandwidth than any other AWG on the market. Coupled with the award-winning industry's state-of-the-art Infinium UXR series real-time oscilloscope, which offers from around 256 gigasamples per second per channel kind of a sampling with 40 to 110 gigahertz bandwidth, along with the extremely low noise front ends, will ensure that you do the right measurements. In addition to this, we do have the optical to the electrical converter, which will extend the UXR testing into the optical domain. The UXR oscilloscopes can also be used for error detection, which includes clock recovery, up to 224 Gbps and beyond. Additionally, there's also the N1000A, the DCAX mainframe with the N1046A 100 plus gigahertz remote head modules, which provide the industry's lowest noise oscilloscope solution for high-speed digital designs. As we saw earlier, data throughput of 800G and beyond, going all the way to 1 terabyte bit and then all the way to 1.6 TB, will be an evolutionary increase from 400G and with basically faster PAM4. As you can see, development for the electrical need are already available with the chip-to-chip, chip-to-module, and then for the backplane projects. The results are the initial definitions for the various high-speed gigabaud electrical links, and optical definitions will follow the electrical developments. Selecting the optical transceivers that comply with the industry standards is critical for data center operators to support speeds of 800G and beyond. Fortunately, the high performance instruments that were used has integrated the software which used for 400G device development and are also capable to support the 800G and beyond device development and test. So specifically talking more about this, we do have the suite of solutions, whether we are talking about the software design or then you get into the validation aspects of it. We do have everything all the way into manufacturing. Digging deeper and talking more about the challenges which would be encountered with the 800G and beyond, as you can see, complex PIC structures with the integrated silicon modulator and PD will require characterization of the electro-optical frequency response. The challenge here is to de-embed the electrical and optical probes which are used with the LCA, as you can see here, which normally requires a calibration up to the coaxial DUT interface. So measurements like on-wafer S parameter testing and group delay with an unmatched broadband detector with or without proper de-embedding of the wafer probe is of utmost importance. As we see, the erroneous group delay ripple, which is also an important parameter which will impact the system performance of the DUT, can be effectively removed by the proper de-embedding of the ripple contributing wafer probe. Our LCA also allows for extension of the coaxial calibration plane to the tip of the wafer probe via what's called as the RF path de-embedding feature. In summary, not only measuring peak frequency response in this particular set of measurements, the measurement described here is also a guaranteed specification with the performance traceability, which is the only reason how peak under test can also be guaranteed. Using our time-tested methodology, we have developed and maintained electrical and optical calibration artifacts with the NIST and PTB standards, which we use for individual instrument performance specification. Whatever peak measurements are done by the designer is traceable to the Keysight specification, which is further traceable to the national standards. To understand more, service providers and data center operators are seeking 800G technology to meet a growing demand in network capacity at a desired cost and power consumption targets. Innovative network devices will enable the revolutionary changes which are needed by the operators to increase the network bandwidth from 400G to 800G and beyond for data centers and hyperscalers with the same number of fibers. The right tools, including the right test instrumentation and software, will enable engineers to successfully test their new devices and also to ensure that it is pretty cost effective. As you can see here, when the data throughput is going to ensure that we have to have the right kind of approach to test 224 gigabit per second design, which is going to drive 800G and beyond. And we are proud to announce that we have the industry's only error detector solution on the planet above 64 gigabaud. That includes a pattern generator and error detector hardware with the UXR series oscilloscope, and also the error detection software which will help you time to market and get to market faster. When the signal is too degraded at the input to the DFE, as we see, the options are to apply a stronger transmitter FFE or a stronger CTLE or both. Optimizing this manually is difficult and time consuming, but we do have tools that can assist you on that. And with the 800G and beyond, this becomes very, very important to characterize and ensure that it all covers all the corner cases specifically, and the designs are pretty rugged. These figures actually show the results after a grid search for the transmitter FFE first precursor, the first post cursor, and the CTLE settings that yielded the best VEC with sufficient eye height. Looking at the final configuration and the pulse response is informative. As you can see, in this case, no amount of CTLE alone could achieve a passing VEC. The biggest issue is the lack of pre-emphasis on the leading edge of the pulse response. The optimal result that is required is for a large enough negative transmitter FFE precursor is to allow the Mueller-Muller criteria to select a point that has zero residual pre and post cursor ISI. This requires a narrow or a fast enough pulse response to place the first precursor at the zero crossing and still be able to fully equalize the first post cursor. There are many transmitter FFE settings that could have achieved the above criteria, but the optimal one had a little bit extra pre-emphasis that allowed for a smaller CTLE setting as well. The optimal combination left the pulse response with only minimal overshoot on the post cursor side, and once there is enough CTLE to allow the DFE to fully equalize the post cursors by not hitting the tap limits, the best solution allows the DFE to take care of the rest. As we see further, the block diagram here shows a brute force method which is used for determining the optimal combination of CTLE and DFE. As you see in this example, the plot of results across all CTLE settings, and there are multiple configurations that yield similar results. The search will have multiple local minima, and there isn't a clear way to determine optimal result without a full grid search. While the number of CTLE configuration is kind of daunting to measure, the real problem is that the transmitter FFE needs to be optimized as well and has far more possible settings. And exhaustive search of the combination would take prohibitively long to measure, so we need another effective way. Even with an understanding of the strength of the three equalizers, tuning them manually to the best VEC/I height is very difficult. So typically what one does is to ensure applying sufficient transmitter FFE, like I mentioned earlier, and to allow the DFE to not be at its limit with the CTLE settings in the middle of the allowable range. Then it allows to find the GDC2 with the best VEC. And finally, then sweep the GDC for the best VEC with the passing I height. A couple of topics here on the way to 224G is worth discussing. Especially when you are talking about the instrument correlation efforts as well as the advances in the noise and jitter that is managed in the context of 112 Gbps and then extend it all the way to 224 gig and beyond. So specifically when we talk about either the real-time scope simplified setup or the bandwidth equivalency, we see that there is a flexible software integrated DSP clock recovery which is effective for anything greater than a high gigabaud. The real-time scope, as you can see, can perform unaliased frequency domain measurements from DC all the way to 110 gigahertz, and it has early access to key functionality for current and future modulation formats. Whether it is error detection capabilities or wideband phase noise analysis or DSP clock recovery, or specifically talking about advanced equalization and analysis for arbitrary burst FEC encoded or SSE modulated patterns. So moving forward, we see that 800G is going to be the next data center speed class or the node which we can envisage, which is going to revolutionize the world. So whether it is specifically talking about 800G design and simulation, we see that 800G is pushing the PAM4 signaling to physical boundaries. Overcoming the resulting challenges in high-speed serial design would actually take months. So unless one gains essential design efficiency through integrated channel and electromagnetic simulation and accurately simulating complex signal links that include jitter, equalization, clock and data recovery with the channel simulator as well as with the IBIS and AMI models in just minutes, which is helped through the award-winning Pathway Advanced Design System or ADS. Keysight Technologies industry first electrical, optical, electrical or the EOE solution will enable the designer to analyze their optical link from end to end by simulating their design within a given bit error ratio target. Talking specifically in summary about the 800G validation test, to achieve 800 gigabit per second link capacity, the designer needs to make trade-off depending on their existing infrastructure cost, the power consumption, space and backward compatibility needs. Our R&D team has a real-time optical transceiver test solution which we have introduced to provide the highest bandwidth and flexibility for reliable in-depth analysis of 800G links. Like I mentioned earlier, the M8199A arbitrary waveform generator will support higher order modulation schemes and with the most accurate UXR 110 GHz oscilloscope with the lowest noise floor will enable the designer to validate the true performance of their devices. Testing physical layer interconnects such as backplanes, cables, connectors, interposers, chipsets and printed circuit boards is no longer going to be very trivial. As speeds increase, the margins reduce, it's going to be a must do rather than good to have kind of testing. Our PLTS or the physical layer test system software and scalable vector network analysis will enable the designer to test their multiple channels at very high frequencies. Talking more about the parametric test for 800G, photonic integrated circuits or PICs in short will allow the next generation 800G networks to yield higher capacity and significantly improve power consumption and manufacturability. One needs to test optoelectric wafer level kind of systems which would involve electrical measurement of sheet resistance and capacitance and optical measurements of attenuation and responsivity and to characterize the PIC material and structure quality. Keysight Technologies photonic on-wafer test solution will help characterize the user's PICs and optical devices. In addition, talking more about the 800G conformance tests, 800G standards like the IEEE 802.3CK 100 Gbps per lane electrical standard would continue to evolve. And we keep to continually update our test solutions to track these standards developments. Our solutions will help validate new test methods and specifications before the standard is complete. So whether it is 400G, 800G or beyond, moving into the terabit range, we ensure that we provide automated test applications that would not require an in-depth understanding of the standards, and we can help reduce the characterization time of your PAM devices from hours to minutes. And last but not the least, when we are talking about 800G manufacturing test, it requires the production of quality components and devices at the lowest cost possible. One needs to needs highly accurate and efficient test systems to help reduce the cost of 800G manufacturing test system by minimizing test equipment idle time, increasing effective system throughput, and reducing the amount of time of the equipment which would be required to meet the capacity needs. So at the end of the day, whatever the requirement is, Keysight is there to help you with our award-winning solutions, as you can see for 800G and beyond. And all the entire test suite is shown in this slide. So before we wind, I would like to summarize the solutions and the various capabilities we offer in the 800G and beyond space. So as we saw earlier, with the 800G comes unprecedented challenges, and then we also saw what are the various techniques which are adopted to ensure that these challenges are met. Whether it is in terms of signal integrity, or you are talking about the various modulation schemes, whether it is PAM4, PAM6 or PAM8, which are going to be the prospective modulation formats of choice. So Keysight paves the designer's way to a successful design with the flexible and scalable 224 Gbps test solutions. So with the move to 800G and all the way to say 1.6 terabit in the data center and hyperscaler networks, interfaces with the 200 Gbps and beyond are beneficial. And the good news is that, like we mentioned earlier, Keysight offers the industry's only 224 Gbps test solution for both electrical and optical testing that will enable you to successfully design pluggables, near packaged optics or co-packaged optics, and other types of formats. As designs get into unprecedented tight signaling conditions, Keysight ensures that it helps you free up your much needed margins and ensures that you get clear insights into the performance of your design. So in summary, whether you want to realize your 224 Gbps slash 800 gig designs or more for any type of capabilities circling around 800G, we provide a comprehensive solution so that you made the right choice of scalable and comprehensive testing through our simulation, all the way to validation, all the way to conformance and manufacturing. So with this, we will move over to the Q&A session. Please dial in the questions in the Q&A box in the console. Before we move over to the Q&A session, we would like to thank you participants for taking part in today's virtual event on Demystify 800G hyperscaler testing tips and tricks. We believe today's session would have helped the participants to get a better understanding into the various facets of deep diving into Demystify 800G hyperscaler testing tips and tricks, and getting the first mover advantage designing and developing your data center and hyperscaler solutions and products. Dear participants, as was mentioned in the beginning of the virtual event, please help fill the survey form and share your requirements, enabling us to serve you better. Also, you can download the various resources on deep diving into Demystify 800G hyperscaler testing tips and tricks from the widget. You can also download the slide deck and please let us know if you need a copy. Now we will move over to the Q&A session. The first question is, can you please enumerate technical challenges of 800G Ethernet? The speed of the previous 400G electrical lanes is doubled to 112 Gbps for the first generation of 800G Ethernet, and then goes to 4 times, that is 224 Gbps in the second generation. Interface chip DSP chips, packaging, connectors, etc. all will need performance improvements or new designs to work at the higher speeds. There are already some corresponding standards in the industry that define 112 Gbps electrical ports, such as the OIF CEI 112G family of implementation agreements, and also the IEEE 802.3 CK standard. Both standards bodies define electrical link requirements for various distances and reaches. The standards which are formulated by the OAF for different scenarios have been initially released, ranging from short distance chip-to-chip connections such as the CI112G MCM or XSR, medium distance chip to module with the VSR, and up to the longer distances through the backplanes and copper cable, especially with the LR or the long range. So taking the CIE VSR as an example, what happens is the loss of the channel from the host IC to the module IC can be as high as 16 dB at the Nyquist frequency, which is very high for chip packaging, PCB materials, and connector performance requirements. So to overcome this particular problem, new optical module packaging and electrical connections have to be developed. And also for specifically talking about PCB losses, which basically scales with the increasing baud rate, that is about 1.5 to 2 times that of the 400G modules, and restricts the usable channel length at higher baud rates. So typically alternative designs employ cable assemblies in preference to PCB material to minimize the loss. So another key factor for 800G Ethernet technology is the data throughput of the switching chip. So currently we see that 25.6 T switching capacity chips supporting 100 Gbps electrical interfaces, which are available as we speak. But with the next generation 51.2 T chips coming in the next 1 to 2 years, we would see that there would be challenges that need to be overcome with, especially when these become reality. So the real challenge comes for single channel 224 Gbps optical port technology that is required to achieve 800G connections with 4 channels. So long story short, at the end of the day, maintaining a high degree of flexibility for both technology choices and the best investment in terms of instrumentation is of paramount importance. Then other things like the bit error ratio of the system also needs to be taken care of, so that equalization and other technological facets are taken care of. So in a nutshell, these are some of the factors that need to be taken care with respect to 800G and beyond. Hope this answers the question. The second question is, what are the typical signal generation approaches which are used to test 800G? The path to 224 Gbps transceiver development typically starts with the performance research at the component level, such as optical modulators and detectors, driver amplifiers, switch chips, and so on. So to test these devices, it requires a high-speed electrical test signal generator with the flexibility to adjust amplitude so as to adapt to the voltage requirements of different devices, as well as parameters like linearity to compensate for the device gain compression, and also modulation formats to study the performance difference of different PAM modulation schemes, as well as de-emphasis to compensate for device packaging and transmission line bandwidths and so on. The most suitable commercial equipment that can be used in this kind of development would be a high bandwidth arbitrary waveform generator, typically very similar to Keysight's popular AWG, for instance, the M8199A, which is a very high bandwidth 4-channel AWG or arbitrary waveform generator, which has a sampling rate per channel which is pretty high at 256 gigasamples per second, and DAC resolution of 8 bits. Whereas it can also do very complex signaling like 4 level, 8 level, or even 16 level or more. In addition, the arbitrary waveform generator can generate different signals by downloading different digital waveforms. So it's easy to perform the signal compensation and impairment, such as adding de-emphasis or jitter, or to compensate for the channel losses the ISI, the intersymbol interference, by pre-distorting the downloaded waveforms. So in a nutshell, the M8199A is a typical ideal signal generation tool for 224 Gbps research, with the ability to provide PAM4, PAM8, or PAM16 or other modulation formats as required, and is pretty flexible to support the development into the various appropriate technologies. Hope this answers the question. The next question is, how is component testing done for 800G and beyond designs? In the development and evaluation of ultra high speed chips and optoelectronic devices, the frequency domain parameters, for example, bandwidth, gain, flatness, and so on, are the most basic parameters to indicate and measure the device performance. So before even digital signals are applied, measurement and analysis of S parameters, which are obtained with the high frequency vector network analyzer, can give a good indication of component performance. This is a particular challenge with components such as the optical modulator and the photodetector. The performance of the modulator will affect the quality of the signal, which is converted from the electrical input to the laser output of the transmitter, and the performance of the photodetector will affect the quality of the receiver optical input, which is converted back to an electrical signal. The current state of the art modulators, which are based on thin film lithium niobate or silicon optical microring modulators, can help achieve bandwidths which exceed 60 gigahertz, whereas photodetector bandwidths can even be higher. So to achieve mature commercial use, these devices must be consistent and stable. So typically, to perform a detailed verification and evaluation of the characteristic of these devices over the entire frequency range, including the frequency roll-off characteristics outside the specified bandwidth, light wave component analyzer, or popularly known as the LCA, with a frequency range above 80 gigahertz is required. Hope I did answer this question. So while we keep getting questions on the chat box, please keep dialing in your questions so that we can answer them one by one. The next question is, what are the tools which are used for 800G design and simulation? 800G pushes PAM4 signaling to physical boundaries. Overcoming the resulting challenges in high-speed serial design would usually take months. And this would also involve essential design efficiency through integrated channel and electromagnetic simulation. Accurately simulating complex signal links, which include jitter, equalization, clock and data recovery, and with the channel simulator and IB's AMI models, would be very easy to just run it in a few minutes or a couple of hours with the Pathwave Advanced Design System or ADS. So our industry first solution, which can take care of both electrical and optical signals, would enable the designer to analyze their optical and electrical link from end to end by simulating their design within a given bit error ratio target. And Keysight tools would also offer virtualized Ethernet design verification solutions that would help reduce dedicated and specialized hardware cost. And this would also include increasing the flexibility. Hope this answers the question. In the interest of time, this will be the last question I will be taking up. In the meanwhile, please keep dialing in your questions so that we can get back to you over email. So the question is, what is the play for overlay networking with respect to data centers and hyperscalers? Overlay networking is the backbone of modern data centers. Hyperscale data centers need to handle the increasing demand of big data, cloud computing, server virtualization, and real-time applications. The data center network needs to scale up and down depending on the growth of the workloads dynamically. To be able to connect to applications which are running in different servers, they need to adapt to changes while the applications would move. And the networking infrastructure also needs to offer provisioning agility. A virtualized network overlay is extremely common to solve these challenges, and that would help enable network segmentation, flexible workload placement, and dynamic provisioning, which is based on demand. Overlay typically ensures that it helps create virtual networks on top of a layer 2 or a layer 3 physical network. And these overlay paths would route the traffic which is coming in and out of the data center and also within the virtual machines inside the data centers. Tunnels are typically used to transport the payloads across an underlay or a physical network that has no visibility into or awareness of the traffic in those tunnels. Data center and hyperscale operators would prefer overlay because it reduces the need for frequent modifications to the physical network while providing more agile deployment of networking resources. Like I mentioned earlier, if there are more questions, we request you to dial in the Q&A box, and we'll make sure that we'll get back to you over email without fail. Dear participants, we hope this session was helpful to you. This session would also be available on demand shortly so that you can go through this virtual event again. Would thank you for participating in this session. As you know, Keysight Technologies is running a series of virtual events periodically, and we'll keep you posted on the next set of virtual events over email and other modes. This virtual event will also be available on demand shortly, and you can also view this virtual event any number of times on demand. And also please share the on-demand details with your colleagues, team members, friends, etc. so that they can register and participate. With that, we'd like to sign off this virtual event. All of you have a nice day. Thank you and bye.